Unit 2.3 is proving theorems. We have a couple of theorems on this page, and we're gonna prove them. This whole two-column proof thing is not on this page, but we're gonna do that. I would have just kind of went to the side and done this in class. The bottom is steps in finding reasons in a proof and then justifying algebra problems, and we'll get to that in just a minute. What I'm going to do is show you how to do a two-column proof. Now, what I'm going to start saying is written down in the textbook later as we do proofs. But we're going to start building some mental vocabulary. I call it brain training as I teach my students. But the midpoint theorem actually says if M is the midpoint of AB, here's the visual, if M is the midpoint of segment AB, the definition of a midpoint, remember, says that segment AM is equal to segment BM. That's the definition of a midpoint. What we get out of it is two equal segments. The midpoint theorem says if M is the midpoint of AB, then segment AM is equal to 1/2 segment AB. Or the distance between, that's what it means if there's no segment symbol above it. The distance between point A and point M is 1/2 the distance between point A and point B. It's fine with me if you use the segment symbol or just the distance symbol. Segment AM is 1/2 of segment AB. Now, how could we do this? How could we prove this theorem in a formal two-column proof? Remember, we said at the very beginning of this course that theorems were things that we can prove using logical reasoning based on other definitions, postulates, or theorems. A postulate is something that we see with our eyes or we experiment and we finally realize that it's true. Let's show you how a two-column proof works. Now, when I do a two-column proof, here's what I say. This is a little jingle that you'll have memorized before we get done, and that is to write the given, prove, and proof. We'll put the statements on the left and the reasons on the right and draw a diagram. Okay? I'm going to repeat that. Write the given, proof, put the statements on the left, reasons on the right, draw the diagram. So we're going to write the given. Remember, the if part is the given. So given that M is the midpoint of segment AB, let's prove that the conclusion, segment AM, its length is 1/2 the length of segment AB. Let's prove that. Now, to do a proof, I say the jingle. We're just going to keep repeating it. You write the given, proof, put the statements on the left, reasons on the right, draw the diagram. We're then going to take what we're given. We're going to mark that in the diagram and write statements and reasons derived from the markings in the notes section. So we're going to read that given statement. It says M is the midpoint of AB, and we say, well, what does that mean? What do I get out of that? Well, what I get out of that is segment AM is equal to segment MB. So I marked that in the diagram, and I'm going to write down what I marked. I marked that AM was equal to BM, reason, and I'm pausing so you can think. What would the reason be? Well, we have the, remember this, word, midpoint. The what you get out of it, two equal segments. It's the word and what you get out of it And so you're going to say definition of midpoint. Now, remember, before you can say definition of, you have to have the word and what you get out of it. So we know that in this proof, before we could say definition of, we would have to have the word. So we would need to put that statement first. Now, the given statement is not always the first statement in the proof. It is in the spot where it's necessary for it to be according to the flow of the proof. We know we need the word midpoint before we say definition of. And we know that we can make that statement because it was given. So we would say M is the midpoint of A, B, given. So we took what we were given, we marked it in the diagram, we wrote statements and reasons derived from the markings in the note section. The next thing we're going to do is we're going to look at the prove part. We're going to think of every possible thing we've ever learned that would allow us to reach that conclusion. We're going to make that proof statement the very last statement in the proof, and we're going to search for a reason. Now, it's the last statement because we're trying to say, given that this is true, what allows me to reach that conclusion? It's like a roadmap telling you how to get there, and when you get where you're going, you don't need any more directions. You're through with the roadmap, you see? So once we get to the proof, we're done. But we have to have a reason to say that AM is half of AB. Now, we've got to think about everything we've learned in this entire geometry book so far that would allow us to conclude that two things are equal. So here we go. We start scanning. Well, we started out with three undefined terms, point, line, and plane. We had the definition of a segment. We had the definition of a ray and opposite rays. We had an angle, and we had congruent angles. Congruent angles, that's two angles that are equal. So that says something's equal. And then we have the definition of a midpoint. That says that two things are equal. And then we have the definition of an angle bisector. That says that two things are equal. And we keep thinking about what gives me two things are equal, but now this has a half. We're going to half something. Now, half something. What have we ever done that half something? Well, we go back to those properties of equality. If you divide by 2, that would half it. So division would half it. Multiplication is not going to half it unless you're multiplying by half, but that's the same as dividing by 2. So when we go through all the things we've ever learned, it seems that the only way we're going to get there is to divide. So I'm going to hypothesize, if you will, that my final reason is going to be division property of equality. I'm going to divide by 2. Now, if I'm going to divide by 2 and get this, see, from here on out, it's just logical thinking. How do I work my way backwards? I know this up here, and I know this down here, but the middle stuff has to give me that reason I'm looking for. Now, remember, division property of equality is 3 steps. If A equal B, then A divided by C is equal to B divided by C. And so then we would need a statement that says C equals C, you see. That sounded kind of weird, but anyway. Well, if you want to know where division came from, you go backwards and multiply. Example, let's say that we had 3x, let's say that we had x is equal to 2y. The opposite of division is multiplication. So if I multiplied them by 2, I would get 2x equal 4y. So that if I divided by 2, I would end up with x equal 2y. You see, if I want to know what I could have divided by 2 to get that, I'm going to multiply by 2 to go backwards. If I want to know what I divided by 2 to get this, then I'm going to multiply by 2 just to go backwards. Well, if I multiply by 2, I'm going to have 2am is equal to 2 halves is 1 whole ab. So if I'm going to say am equal half ab because I divided by 2, then it had to have come from 2am equal ab. 2am equal ab. Okay? Well, you can say, well, I can do that, but I need a reason for that. How am I going to get 2, let's go to the picture, AMs is equal to an AB? You can kind of start seeing it, can't you? 2 AMs is equal to an AB. But you see, I can't take the picture and say that, you see. From the picture, all I can say is that AM plus MB is equal to AB. Now, what is it that says AM plus MB equal AB? Well, that's segment addition. Segment addition will allow me to make a statement close to what I want. It will allow me to make the statement that AM plus MB is equal to the whole thing AB. But I don't really want it to say AM plus MB. I would rather have 2 AMs. That means that I need to get rid of that MB. Well, the only way to do it is to substitute. This statement we already have says AM is equal to MB. So I can replace that MB with this AM and have 2 AMs by substitution. Now, all of a sudden, there's not any blanks to fill in. Did you notice that all of a sudden, there's not a blank? I said to make this statement, I'm going to try to use the reason division. But I said if I'm going to say division, I need to know where it came from. So I'm going to multiply to go backwards. But if I'm going to make the statement of where that came from, I need a reason for that. And so I went to digging around in the picture and I saw segment addition and I made that statement. And I saw that these were equal, so I could make a substitution and I got a reason. And all of a sudden, all my blanks are filled in. I'm going, hey, I must be done. Looks like I bridged the gap. And so what I have my students do, and I know this is getting to be a tangled web here just a bit, is to check the statements and reasons from the bottom up. In other words, if I'm going to say division property of equality, then I need to have the original statement. I need to have the resulting statement. And I can, if I want to, in here say that 2 is equal to 2 by reflexive. You see, I could sneak that right in the middle there. 2 is equal to 2 by reflexive property. Some books will put that in there and some will leave that out. If I'm doing an algebraic proof, I usually put it in just to have my students practice reflexive. But a lot of times it's left out because it's kind of understood to be there. So those 3 statements prove distributed. To say substitution, I needed the statement that AM plus MB is equal to AB. I needed the statement that said they were equal because you can't substitute unless they're equal. And then the resulting statement, so it took those 3 statements to make this reason. Segment addition is in the picture, so that's justified. Definition of a midpoint, to say definition of, I need the word and what I get out of it. They're both there, so that's justified. Midpoint given. Every reason is justified in the statements above it. Every statement is needed to justify some reason, so I must have it all in the right order. So I did all my scratch work over there, and it may get a little bit interesting, especially when I go over it 2 or 3 times. And so we're going to transfer that over here so it flows. Now, it could be that as you analyze that, you need to do some rearranging, but in this case, it all looks like it's supposed to. So statement 1, we would have M is the midpoint of segment AB. Reason for statement 1, reason 1 would be given. From the definition of a midpoint, we got that segment AM was equal to segment BM. We had the word midpoint and what we got out of it, so we said definition of a midpoint. By segment addition in the picture, the two little segments add up to be the whole big segment. We made the statement that AM plus BM was equal to the whole thing AB, and that was segment addition. And I would ask at this point, do you remember segment addition? If you don't remember it very well, then you're not studying the geometry book every night. You need to study this book daily so that you memorize every definition and postulate and theorem with understanding and a visual in your mind of what it's like. If you're not, then you won't be able to do these proofs because it won't hit you. There's segment addition, or that looks like substitution. You can't go through the list of everything we learned if you never learned all of that stuff and if you don't continue to review it. Statement 4, we got that 2 AMs was equal to AB because we replaced the green BM, with the red AM and had got 2 AMs by substitution. We could show our work and show that 2 is equal to 2, and we divided both sides by 2, and that would be a reflexive property. Or we can just leave it understood that we divided by 2 and get AM is equal to 1/2 AB by the division property of equality. Any questions on that? Proving theorems. This is a theorem because we used mathematical reasoning to go from something we already knew, that a midpoint gives us 2 equal segments, to our new conclusion that one segment is half of the whole thing. We proved it not by experimentation and measurement, but we proved it with a logical reasoning process using statements and reasons and theorems and definitions and properties. Okay? Any questions on that? All right. Just like we proved the midpoint theorem, we could use the same logic to prove the angle bisector theorem. You would use angle addition, substitution to get 2 of them, division to get down to 1 of them is half of the whole thing. Same concept, it's just angles. And I'm not going to go through that proof. It would be the same kind of proof. So if ray AB bisects angle CAD, then we can conclude that this angle must be equal to that angle, If it is, then one of them is half of the whole thing, and really the other one's half the whole thing too also, right? So we could conclude that the little angles are both half of the big angle. So we could say that angle, and I've got to reset my pen here. Excuse me just a second. I could say that angle CAB is equal to 1/2 of the whole big angle, angle CAD. And I could also say that the other little angle, angle DAB, is equal to half of the whole big angle, angle CAD. And that is the angle bisector theorem. And again, it could be proved in the same way that we proved the midpoint theorem, just using the definition of an angle bisector and angle addition and substitution, rather than the definition of a midpoint segment addition and substitution and division. Okay? Now, sometimes in textbooks, they give you the statements in a proof, and all you're going to do is look for the reasons. And if that's the case, then this is a little lesson, a little set of steps you can use to try to be able to find those reasons. And as we just do reasons only, that's going to help us with the two-column proof thing. The first thing we're going to do, as we said in the other, is to mark the given in the diagram and write statements and reasons derived from the markings in the note section. That's going to be important to do whether you're doing an entire proof or reasons only. Now, when you look for reasons, it's important to look in these places in this order. We're going to look first at the given. There's no sense in analyzing a whole bunch of stuff to try to figure out what the reason is if it's given. See? And then second of all, you need to look at the diagram, because sometimes the only way you're going to find a reason is the diagram, like segment addition is in the diagram. Vertical angles are equal would be in the diagram. Angle addition would be in the diagram. So there's no sense in studying the statements for a long time when you're supposed to see it in the diagram, you see. So we look at the given first, because that's the no-brainer when it's right there. Then the diagram second, because if it's there, you're never going to find it in the statements, and you're going to waste a lot of time looking. It's easy to look those two places first. And then if it's not in those places, then you start the intensive digging into the statements above it. Now, when we look into the statements above it, we're going to use a little bit of logic. We're going to ask ourselves, well, what do they have in common? Just like a while ago when we did a substitution, I highlighted in green that the second part of the given looked almost like the conclusion. The only difference was there's an angle 2 where the angle 1 was. Okay, and so we said, hey, that's a substitution. We figured that out pretty quickly by comparing. So we want to know, what do they have in common? What do they have different? And what would I need to do to change them to make them look alike? That thing that you would have to do to change them to make them look alike is the property you're going to use. And so you're hoping something will pop out. What says that I can do that thing that I need to do to change them to make them look alike? Okay? When you justify algebra problems, the first one's always given, because you're given an algebraic equation and then you're going to solve. It is important when you do that to think about the order of operations horseshoe on page 33 of my algebra textbook, which says, do anything you can in the order, please excuse my adherent solely to simplify, looking for distributive property and combining like terms. Get the variable you're isolating on one side of the equal sign, remembering to change the sign when you cross over, and then undo in the reverse order. Sally out during my excuse, please. When you're doing, you may be distributing or combining like terms. When you're undoing, remember that's using addition property of equality, subtraction property of equality, multiplication and division property of equality. If you undo addition by subtraction, you're using the subtraction property of equality. Uh, so, one of the things we do is we say, well, what disappeared? Example, if we had 4x equal 12 and all of a sudden there's an x equal 12, you might say, well, what disappeared? Well, the 4 did. Well, what would make that disappear? Well, division gets rid of multiplication. Whoops, and that would be a 3, excuse me. And you would say, oh, that's the division property of equality. Okay? Or you might have 3x minus 6 is equal to 12. And then there's a statement that says 3x equal 18. And you're saying, well, what disappeared? Well, the minus 6 did. Well, what would make that disappear? Well, adding 6 to both sides. And so that's a result of the addition property of equality. See that? So how did they change and what property allows them to change? Now, it could be things like commutative property, associative property, reflexive property, substitution property, some of those other properties from algebra that we learned over on page 28 to 29a. Okay? So let's look at the daily work on Unit 2, 3. Remember, in an algebraic equation, the first thing is always given. In other words, how did we reach this conclusion? Well, they gave it to us. It's a given problem. But then when we go from the first statement to the second statement, we want to compare them to see, well, how are they the same and how are they different? Well, if we compare how they're the same, we've got an 40x and equal and a 40x and equal. They're the same on that side, but on the right side, they're not. And so how are they different? Well, they're different in that this had a parenthesis and this one does not have a parenthesis. Well, what would make that parenthesis disappear, we would ask? Well, that operation multiplication is crammed on that parenthesis. If it's crammed on a parenthesis, we check for distributive. We would distribute and go 3 times x is 3x, 3 times negative 6 is negative 18. So this statement was a result of using the distributive property of equality. As you continue down, you would look at this statement and say, well, where did that statement come from? Well, we've got to be thinking algebraically. Remember the order of operations horseshoe? Do anything you can to simplify in the order. Please excuse my dear Aunt Sally looking for distributive. There was that. And combining like terms. When you've done all you can do to simplify, we said, then you look at the bottom of the horseshoe, which says, get the variable you're isolating on one side of the equal sign, remembering to change the sign when you cross over. So what we would have done is subtracted x from both sides. 3x minus x is 2x minus 18 equal 40. So this is a result of having subtracted x from both sides. When you subtract something of equal value from each side, that is called the subtraction property of equality. And you can go from there as you think about what you would do next using the order of operations horseshoe to solve that algebraic equation. Okay? All right. The next is a geometrical proof, and we're going to kind of look at this one. Here's what I've said that you should do. You should take the given ray FD bisects angle CFE. We will create a note section. If we were doing the whole proof, I would go ahead and say ray FD bisects angle CFE, reason given. And I would do that because I'm fixing to take the what you get out of it, two equal angles, when it says that ray FD bisects angle CFE. What you get out of an angle bisector is two equal angles. I would mark that angle 3 is equal to angle 2. And I would say that angle 3 is equal to angle 2. And my reason would be, since I have the word and the what you get out of it, definition of an angle bisector. And I would already have that in my notes section. And then I would go to the next given statement, angle 1 is equal to angle 2, and I would mark that in my diagram, that angle 1 is equal to angle 2, and I would put the reason for that, which would be given. And my brain would kind of go wild here saying, well, 3 is equal to 2 and 1 is equal to 2, so 1, 2, and 3 are all equal, and that has to have something to do with substitution or transitive, right, based on what we know so far. So my mind's already thought that. 3 is equal to 2, and 1 is equal to 2, so 3 is equal to 1, or 3 equal 2, so 2 equal 1, so 3 equal 1, okay? So we've got all that stuff written down. Now, we're not writing the whole proof here. We're going to help you lead into that by getting you good at marking things on the diagram, writing statements and reasons derived from the markings in the notes section, and then coming over here and writing reasons. So when we say, okay, what is the reason for this? Well, the first place we're going to look is in the given, because we'd want to look there first. If it's there, why go anywhere else? See, that was given. And then we read the second statement, angle 3 is equal to angle 2, and we look first in the given, and it's not there. We look second in the diagram, and it's actually marked in the diagram that 3 is equal to 2. Now, if we marked it in the diagram and it wasn't in the given, then we must have written it down here in the notes section. And there it is, angle 3 equal angle 2, definition of angle bisector. See, it was a whole lot easier to go ahead and write it down as we did it, and then we don't have to try to figure it out. It's already figured out. And then we get that angle 2 is equal to angle 1, and we say, well, is that in the given? Well, no, it was 1 equal 2 in the given. But you got 1 equal 2, 2 equal 1, 1 equal 2, 2 equal 1. What happened? Well, we flipped it over. What property says you can flip it over? Well, that's the symmetric property of equality. Symmetric property of equality. You see, we needed that to happen because you can't see how we went from 3 through 2 to 1 if you don't have the 2's back to back there, see? So we rearranged that so it would flow, and we could see that we're going from angle 3 through angle 2 to angle 1, and we reached the conclusion that angle 3 is equal to angle 1 by transitive property. We transferred from angle 3 through angle 2 to angle 1. Let me show you that again. We transferred from 3 through 2 to 1 and got 3 equal 1. Well, you may say, but I was thinking substitution, because if angle 3 is equal to angle 2, then I could put that angle 3 in place of that angle 2, and I could get there by substitution, and you're correct. So that could be substitution property of equality also. Any questions on that? Okay. And we'll leave that second proof for you to do, whoops, excuse me, to do on your own. Okay. I'm making bad clicks. All right, let's look at a few more of these. Let's go to number 14. Number 14 says if E is the midpoint of AI, then AE equal 1/2 of AI. Now we have the word midpoint, but we don't have what you get out of it, because what you get out of E being the midpoint of AI is that segment AE is equal to segment EI. That's definition of a midpoint. So this is not definition of, because we don't have the word in what we get out of it. Remember that if we have midpoint and the fact that one is half of the other one, that's a theorem that we proved based on the definition of a midpoint. This is called the midpoint theorem. Remember that? Midpoint theorem. Okay. Let's look at number 16. It says if ray OZ bisects angle POU, well, what do you get out of that? Well, an angle bisector is a ray that divides an angle into two equal adjacent angles. So we reach the conclusion that angle 1 is equal to angle 2. And the reason is going to be, well, let's see what we got. We got the word angle bisector. The what you get out of an angle bisector, angle 1 equal angle 2. We have the word and what you get out of it. And so we say definition of. Definition of an angle bisector. Okay? Any questions on that? You see the difference in definition of and midpoint theorem, or definition of and angle bisector theorem? Okay. Now, I'm going to let you do that last two-column proof yourself. I think you need that experience. Don't forget to take what you're given, mark it in the diagram, write statements and reasons derived from the markings in the note section. That keeps you organized, it gives you a visual, and it gives you some reasons to start with. The next little section here, and I encourage you as a student to take this serious and do a good job of it, and teachers to encourage your students to do this, because this is going to get you the ability to use a protractor, to use a compass, to actually measure in inches and know where a fourth is on a ruler and an eighth is on a ruler and all of that. It's also going to help you make discoveries from pictures. Now, what's going to happen here is you're going to measure angle 1 and get a certain degree, whatever that is, and you're going to measure angle 2 and get a certain degree, and you're going to find that angle 1 and 2 are the same degrees. And then you're going to measure angle 3 and get a certain degrees, and angle 4 and get a certain degrees, and you're going to find that angle 3 and 4 are the same degrees. And so we discovered that those angles that are opposite each other are equal. The name for those angles are called vertical angles. And so we reached the conclusion, that was nice, let me start again. We reached the conclusion that vertical angles are equal. So what we're doing is we're using measuring devices to make conclusions, and we're going to have a rule about that conclusion on the next page. We're basically discovering the upcoming lessons. Again, I think it's very important to do this because it gives the student a hands-on visual of the theorem itself, and it helps them learn to use measuring devices. Okay? So if we were to go to, just so you know, students, and just so you know, teachers, when your students have trouble knowing how to fill in the blank, or when you students have trouble knowing what to put in the blank right here, well, that would be understandable because you haven't learned that rule yet. But you should have gotten the concept that those angles opposite are equal. So if we go to the next lesson, see, special pairs of angles, then what we have here is vertical angles. We figure out that angle 1 and angle 2 are equal. Angle 3 and angle 4 are equal. And so what we're doing is we're having the student figure it out before it's ever presented in the next lesson, you see, by measurement. So they're getting hands-on experience measuring, and they get a visual of the rule we're going to learn next before we ever learn it. Some of the rules we're going to do proofs of, but the student will have done that with their hands first. And hopefully this will give us a better mental image of the things